Welcome to Mechanics of Fluids tutorials, and in this video lecture we are going to discuss about what is vortex flow and what are its types. So first, what do you mean by vortex flow? So vortex flow is that type of flow in which the fluid particles move in a curved path or rotational path. Okay, that is the definition of the vortex flow. So once again we try to write the definition. So what is the definition we can give? Means it is that type of flow. It is that type of flow in which fluid flows fluid flows in a curved path or in the form of rotation. Okay, this is the definition we can give for the vortex flow. Okay, it is that type of flow in which the fluid particles move in a curved path or in the form of rotation. So there is a vortex flow. And what are the different types of vortex flow we have that we need to know? So first one is forced vortex flow. Forced vortex flow. And second one is free vortex flow. Free vortex flow. Okay, these are the two types of the vortex flow we can consider in a pipe or channel. So here, what do you mean by forced vortex flow again? What is forced vortex flow? So what is the definition we can give to the forced vortex flow? Means here, whenever the fluid of a particular mass moves in a rotational form with some external force, so with some external aid, if we are making the fluid to flow in a circular path or curved path or in the form of rotation, then that type of flow can be called as your forced vortex flow. That means we'll create some external torque to the fluid flow to move in a rotational form, so then the flow becomes vortex flow. So what is the definition can be given to the forced vortex flow? Means if any external force or external torque is used to rotate the fluid flow rotate the fluid flow, then the flow can be called as forced vortex flow. Forced vortex flow. Okay, with the help of some external force or torque, we are creating the rotational motion of the fluid. So then that type of flow is called as your vortex flow. Okay, and if we consider a fluid of mass m, a fluid of mass m, and which is rotating with angular velocity angular velocity omega at a radial distance of at a radial distance of r. So we are considering a fluid mass that is of m and that is rotating with an angular velocity omega at a radial distance of r. Then the tangential velocity we can write it as, so what is the tangential velocity we can write, so v is equal to, can be written as omega into r. This v will give us the tangential velocity for the rotation of the fluid flow. Okay, that is the relation between velocity and radius in a forced vortex flow. And what are the examples we can consider for forced vortex flow means, uh, what are the examples we can consider, that is one we can take liquid inside a container, liquid inside a container, and that is rotating, that container is rotating at a particular speed, at a particular speed, that is forced vortex flow. And similarly the second one we can consider flow of liquid, flow of liquid inside the impeller, inside the impeller, inside the impeller of centrifugal pump, centrifugal pump. One more example again we can consider flow of water, flow of water through the runner of turbine, through the runner of turbine. Okay, these are the examples we can consider for the forced vortex flow, for which we'll use some external aid to rotate the flow of the fluid. Okay, so that is about forced vortex flow. Next we go for discussing about free vortex flow. So again we try to discuss about free vortex flow, free vortex flow. So free vortex flow is opposite to the forced vortex flow. So in forced vortex flow we are using some external force or torque to rotate the flow of the fluid, but here without using any external torque or force, the rotational flow of the fluid should be taking place. So then the flow can be called as your free vortex flow. So what is the definition we can give means, it is that type of flow, it is that type of flow, sorry, it is that type of flow in which no external torque or force, no external torque is used to get the rotational flow of the fluid, rotational flow of the fluid, that is the free vortex flow. So without any external agency we are getting the rotational motion for the fluid flow when it is flowing through any particular pipe or channel. So that type of flow is called as your free vortex flow. Okay, so here to get the relation between again velocity and radius, we need to consider a fluid particle, we need to consider a fluid particle of mass m and which is rotating at a radius or we can consider a radial distance from the axis of rotation, radius as r, and the tangential velocity as v. Okay, so we need to consider a fluid particle which is of mass m and it is rotating at a radial distance r from the axis of rotation and as with the tangential velocity v. Okay, so to get the relation in between velocity and r, we need to consider one condition. So what is that condition? Means in the definition we are mentioning that there will be no external agency required to get the rotational flow for the fluid. So no external torque means we can make the external torque is equal to zero, or we can make the rate of change of angular momentum, rate of change of moment of angular momentum must be equal to zero. So that means here the condition is the rate of change of rate of change of moment of moment sorry, here we need to consider moment of momentum, or angular momentum. We can consider rate of change of angular momentum must be zero because it is a free vortex flow. Okay, so first we try to write the momentum. So what is the equation? We know that momentum, it is a product of mass and velocity. So momentum is equal to mv, we can write. And next we need to take the moment of momentum. So moment of momentum means here momentum into perpendicular distance we need to consider. So momentum is mv, and what would be the perpendicular distance? Means that is the radius or radial distance from the axis of rotation. So that is into r, we can write it as. So moment of momentum is mvr. So again go to the condition. What is the condition? The rate of change of momentum must be equal to zero. So this is the moment of momentum. The rate of change of this moment of momentum must be equal to zero. So what we can write means here, next step we can write it as rate of change, that is d by dt of momentum mv into r must be equal to zero. So by integrating the equation on both sides, by integrating the above equation on both sides we need to integrate. So when you integrate both equations, that means integral of d by dt of mv into r, and that is equal to integral of 0. So when you consider integral and differentiation, this integral differentiation gets cancelled. Then we'll get mvr is equal to integration of 0 is constant. So mvr is equal to constant. And when you observe this m, v and r, velocity is variable and the radius can be also variable, but mass of the fluid is, or mass of the fluid particle is constant. So finally velocity into r is equal to, we can write it as some constant by m. So both are constant only. Finally we can write it as vr is equal to constant. So the relation between velocity and radial distance for the fluid particle from the axis of rotation can be written as Vr is equal to constant. So velocity into radius is equal to constant for the free vortex flow. Okay, these are useful for analyzing the fluid flow under fluid kinematics. So this is about vortex flow and its types. Those are forced vortex flow and free vortex flow. So I hope you understood this explanation, and if you have any doubts, please feel free to give a comment to my video. And don't forget to subscribe to my channel, and please share my channel and suggest my channel to your friends. And once again, thanks for watching my video. Thank you all.